Okay, recall that the derivative of a function at a point gives us the slope of the graph of that function at that point. Once we have the slope, we can find the equation of the tangent line if we want and go with and work with that. So today we're going to work with this idea just a little bit more. And so let's begin by just reminding ourselves of the relationship between the slope of a line and the change in x and change in y between 2 points on that line. By definition, the slope is equal to the change of y divided by change in x. If this were 6, for example, and this were 2, then the slope would be 3. Or if you want to, you can multiply through by change of x and you get the change in y is equal to the slope times the change in x. Sure enough, 6 is equal to 2 times 3. So if you take this slope, if you take this change and multiply it by the slope, you'll get that change right there. That's key to remember that in everything we're going to be doing today. Okay, so the first thing to do is let's use this idea to find the value of the square root of 105. We want the square root of 105. And the way we're going to do it, of course you can stick it into your calculator and get it easily enough, but we're going to use this to illustrate the use of tangent lines. So the way we're going to do it is we're first going to take the derivative of this function. So, of course, the derivative is 1/2 x to the minus 1/2, which is the same as 1 over 2 times the square root of x. And then once we have that, we're going to find the derivative at some point close to 105 for which we know the exact value of the square root. And I chose something which is hopefully pretty obvious. If you start there at 100, we know the square root of 100, of course, is 10. So here you are at the point 110. And so we're going to find the slope at this point. Once we find the slope, we're going to find the equation of that tangent line. And then notice that that tangent line stays fairly close to this graph for at least a little ways around 100, okay? So we're going to use that to approximate this value here. We're going to use this value of the line to approximate the value of the graph. So let's go ahead and do it. Easy enough. We first need the slope at this point. Slope at 100 is 1 over 2 times the square root of 100, which is, of course, 1 over 2 times 10, which is 1/20. Now, how do we get the equation of the line? Recall, it's going to be y minus 10 equals the slope times x minus 100. Or, if you solve it for y, plus 10. So we want this value of this line at 105. So if we put in y at, let's say, 105, I'll write it like that, is going to be what? 1/20 times 105 minus 100 is 5 plus 10, right? So there it is, and if you were to calculate that, you're going to get what? So that's 1/4. 1/4 plus 10 is 10.25. So notice that this approximation we have is a little bit bigger than the actual value. So go ahead and take your calculator if you have one handy. Put in the square root of 105, and notice that the answer you get will be less than that one. But notice how close it is. I think you'll be surprised, maybe somewhat impressed, how close we are to the actual value. Okay, so that's one example of using tangent lines to get approximations for the function at a little interval around the place where you're taking the value and taking the derivative. Okay, let's look at a little more generally what it is we're doing here. If you just have some function here, we know, remember this, that the derivative, let's see, I'm going to erase all this except the very last bit here. We know that the definition of the derivative is the limit. We used to use an h, but I'm going to use a little delta x in this case. I'm going to use delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So in other words, here you are at x. I'll make it far enough away just so you can see it. Here's an x plus delta x. So this change right there is delta x. And so what did we do? We took the change in the values of the function, that's that, divided by the change in the values down here, this minus this, which is right there, and then we took the limit as delta x goes to 0, and that limit is by definition the derivative, the slope of the tangent line at that point. So really, what we're doing here is we're really kind of just saying that since this limit is by definition the exact value of this thing, if you don't take the limit as delta x actually goes all the way to 0, but just allow it to kind of stay close to 0. So now we're not pushing it all the way in, but we're just having it be close to 0. Then this will not be exact, but at least it'll still be an approximation. Okay, it'll still be an approximation. So in other words, if you were to multiply through, you would get f of x plus delta x is approximately equal to, if you bring this over, you're going to get f prime of x times delta x plus f of x. And notice that's exactly what we have here. We said right here, we basically, our function that we were dealing with earlier was the function square root. So we had that the square root of 105 is approximately equal to the square root of 100, which is 10, plus the derivative at 100, which is 1/20th, times the change in the x values, and the change in the x values for us was 5. See that? So basically, in doing this tangent line approximation, we're basically just taking the definition of the derivative, and we're just saying, okay, get rid of the limit and make this into an approximately equal sign, and then just solve for this, and you get an approximation for the answer. Okay, so that's just really all there is to it. That's really all there is to it. So so let me get rid of this. And so what we see here, using this picture, is that this difference right there is f of x plus delta x minus f of x. And we see that this difference right here is pretty close, same as what I just talked about, to what you get if you take the slope of the line right here, the slope of the line, is going to be f prime of x, and you multiply that by the change in the x value, which is delta x. Okay, so the change in the value of the function is approximately equal to this. So what we do is we call this difference right there d of f, right there. That's just it's how much the function changes, approximately how much the function changes as you move from here to here. So in other words, this is approximately the case, but this thing right here is, by definition, f prime of x times delta x. Okay, so you take the derivative there, multiply it by delta x, and you get this change right there. And then if you want this value, you just add this change onto that value to, of course, get something which is approximately that value. So just one other way, just to confuse you even more, notice that we have two different ways of writing the derivative. Okay, here's one way of writing the derivative. Here's another way of writing the derivative. Okay, if you think of it this way, that the derivative is this infinitesimal change in the y value over the change in the x value. That's what the derivative is. So just like we did with those lines earlier, if you just multiply through by dx, you get that the change in the y value is the slope times the change in the x value. So actually, either one of these, you'll see them as the definition for df. It's called the differential of f, but it just means that it's the slope times the change in x. So here's what you should have in mind. This change right here is what you get by taking the slope times this change will give you this change. One more time. You take this change right there, multiply it by the slope, which is this, and you'll get that change. Okay? So that's the idea of the differential. Let's look at one more problem where you have maybe used differentials without even knowing about it. Suppose you have a big spherical object, possibly a water tower or something like that, and you wanted to paint it. And so you wanted to paint it with a coat of paint, and you want to know how much paint you need in order to paint this whole thing. So a couple of definitions you need. The volume of a sphere is 4/3 pi r cubed, and the surface area of the sphere is 4 pi r squared. Okay? So what are the ways this radius is r right here? And suppose that after you paint it, it now is, you've painted it with a thickness of delta r. Okay, there's a little thickness delta r. That should be uniform all the way through. Question is, how much paint do you need? Well, one way of doing it is to say, well, let's take the surface area and multiply the surface area by the thickness. After all, if I wanted to paint this board right here, all I would need to do is take the surface area of it and multiply it by, say, a 1/4 of an inch of paint, and that would give me how much paint I needed. If I wanted to paint it an inch thick, then I could go out a full inch, and again, all I do is take the surface area and multiply it by the thickness. So here we go. So the amount of volume of paint, let's just go like this for the volume of paint you'd need, would be 4 pi r squared times delta r. There's the amount of paint you need. Another way of getting the amount of paint, though, would be to say, well, let's first find the volume of this sphere, and then we'll take the volume of the bigger sphere, and we'll subtract the smaller one from the larger one. So then what we're doing is we're saying, hey, it's equal to the volume of the big one. I'll write it as let's just write it all the way out here. Well, I'll write it like this. The volume of R plus delta R minus the volume of R. And so if you put both of those values in for R here and subtract the two, you'll get the volume of paint there. So question is, here I should say this is what will happen if you try it. You'll discover that these two answers that you get are not the same. Okay, in fact, this one is just a little bit bigger than this one. And why is that? I always like to enjoy letting my classes ponder this one when we do it, because it certainly seems like they should be the same. But here's what's going on. If this is R, and this is V of R, then what does this function look like? It's a cubic function, looks something like that. And so let's suppose that that's the volume of the original water tower. And again, I'll move this a ways away just to emphasize the difference. And this is going to be R plus delta R. So this change right there is delta R. Well then, if you want the true amount of volume that you're going to need, you need to take this value right there and subtract that value right there. And that's going to give you the total amount of paint that you would need. However, if you wanted to do a tangent line approximation or a differential on here, what do? You take the derivative at this point and you multiply the derivative by delta R. What is the derivative of this function? Let's see. Well, dV dr is, bring the 3 down, 3 cancels with this, you get 4 pi r squared. There's the derivative. Does that look familiar? Look at that. What's going on here? There's the derivative. And so now you do what? You take the derivative. How do you get this approximation? You take the derivative and you multiply it by your little delta r. So your little dv, this right here, here's your dv, is just going to be the derivative, which in this case is 4 pi r squared times delta r. And that's going to give you this approximation to the true amount, which notice is exactly what we had up here when we tried to just paint it by taking the surface area and multiplying it by the thickness. That's exactly what we got. That's the amount of paint you need. So it's kind of cool. It just shows that when you did this, you were doing a linear approximation without even thinking about it. It still raises the question though, why doesn't this give us the exact answer? As I just mentioned, it certainly seems reasonable that if I want the volume of paint needed to paint this board, I just take the area of the board and I multiply it by the thickness. There is a difference though between painting this board and painting a sphere. If I were to paint this board really thick, I could just keep painting it layer upon layer upon layer, and as I go out farther and farther and farther, this surface area always stays the same. So I really do. All I need is the surface area times the thickness, and that'll give it to me. However, for a sphere, if I were to break this up into smaller measurements and keep painting layer upon layer upon layer, every time I paint the new layer, unlike this board, the new layer is going to have a greater radius to it. So in other words, as I go out from this sphere, this radius is increasing. Not true of the board, the area stays the same. But as I move out from the sphere, the area increases. So there's the difference. So there's the difference, and that's why this is an approximation, whereas that's the real value. Okay, so there's a good explanation of differentials and tangent line approximations, and I think you're set.